Hi, it's Clark on Temptress. Today in the prop shaft alternator project, we're gonna wake the beast. We're gonna make it make electricity. Okay, let's wake the beast. I've got the alternator bolted down to my desk here so that I can reach down and crank it. I've went into the details of all this in the last video, so we're gonna jump over that. When you see my arm go down and my arm spinning around, that's what I'm doing, turning this crank. We've got the three phases brought out to these blue, green, and yellow wires, and we'll take those up to the desk because today everything interesting will be electrical. And well, let's do that. Let me bring you up here so you guys get a nice close view. And I think for this video, I'm going to wear glasses because everything's going to be close. This is a three-phase rectifier done with Schottky diodes. I'll give you a look here to the circuit, but it's pretty simple. The diodes, there's a pair for each of the three input AC phases, and they go in the same direction. They all end in this and this one being the positive, as you can see, and this one being the negative. The rest of that's a heat sink because diodes have a voltage drop, and when current goes past the voltage drop, it makes heat. So you have to get rid of the heat. We'll be trying to address that later. Foreshadowing here. Okay, so we've got our three phases coming out. I think a little more about that is in order. So remember, there's three sets of coils in the stator. So you have the one coil, the two coil, and the three coil. In reality, there were multiple ones spread out, multiple twos spread out, but remember, because of the magic of the magnets being essentially 120 degrees out of phase with each other, on one cycle, they can all be thought of as one. There's two ways you can hook these coils together, because of course every coil has two free ends. In the alternator world, they call these two ways star and delta. So if I take all the poles, all the one ends, and bring them together, and then I grab the free ends and take them out, I end up with what's called a star. As you can see, it kind of looks like a star. It starts in the middle and bursts outward. For every phase end, there's no path to the center anymore. It has to go through the other two. But the average of these two kind of becomes the ground for this one. But there's a little more to it. Since we're going through both of the others, we step the voltage up. So when you use the star configuration, you get more voltage. But the path goes through more coils, so we end up with higher resistance. Now the other way you can do it is called the delta setup. And if we were to wire up a delta, it would look like this. We would take the common end of the one and hook it to the outside of number two and bring that out. And then we would take the common of number two, bring it to the outside of number three, and bring that out, and the same here. And bring that out. Now, we have a different situation where we can actually see this coil separately, because this one is essentially hooked to the inside, and that is hooked to the outside of it. We can see this one separately and this one separately. In this setup, we don't get the help of the other coils, so the voltage doesn't go up. But the resistance also doesn't go up. We get a lower resistance. In essence, if you could spin really, really, really fast, this is the better way to do it. If you can't spin so fast and you want one more trick to bring up the voltage, the other way is the one to do it. Now, I'll leave it to the viewer to figure this out, but with a little bit of switching and a relay or a knife switch or whatever, you could bring all six ends out and make that change on the outside of the alternator. And you could make an alternator that is optimal for low RPM and optimal for high RPM. If you did that, you could have a wind generator that makes a goodly amount of power at low RPM, but instead of getting the drop off it normally does as the wind gets faster. I mean, you always get more power as you spin faster, but not at the same growth rate you would hope. You can flip that switch and now you've got a high-powered alternator. So I'll leave that up to you, but it's doable. Okay, enough drawings, let's play. So we're going to take our rectifier, we're going to take the 3 fields and connect them to the AC inputs. And I think that's all I'm going to do right now. Okay, let's play with the oscilloscope. Take a look at it. That ought to do. This is only a 2-channel oscilloscope. Had I bought a 3-channel, it would be great for this, but 2 channels fine for me for most of my electronics needs. I didn't think ahead apparently. So let's hook up one of the phases and see what happens. I'm going to hook this up to the yellow. We'll ground it out temporarily here to the green. So we're going to kind of get a little of the difference between the 2 of those. And we'll give it a crank. And look at that. Nice sinusoidal shape. Isn't physics grand? We did something mechanical and look what it made. That's AC power, folks. Now let's take the next phase. We'll hook that to the blue. And let's give that a crank. And look at that. We've got the 2 phases slightly out of whack with each other. Had we hooked another one to the green, you can imagine what would happen. We would just have one more phase. Another 120 degrees forward. Well, that's AC power. That doesn't do a lot for us. Let's move our probe. In fact, just for fun, I think I'll leave the yellow one on the yellow. And I'm going to put the other probe on the DC side. So now when I crank it, we get a little different shape. Try to crank it steady here. In fact, let me take a snapshot. All right, good. Now I don't have to crank anymore. So what do we get? If we look at the yellow, remember it used to go down and back up and down and back up. What we have here is it's cut off because of where we've got the negative connected. The diodes aren't letting it pass in that way. So on the purple, we're getting what comes out of the diodes. And that's pretty flat. In fact, I should be able to tell its voltage by playing around with the cursor here. If I crank the cursor up, it's telling me that I'm starting here at 0 volts. And I'll crank it up to kind of the middle of that line, and I'm seeing 10.4 volts. So right now, 10.4 volts at that slow speed that I was cranking is coming out of here. DC power. Pulsy DC power, but DC power. Hey, let's play with that right now. This is a capacitor. Let's hook that up. So here's the positive pin. And do not want to do this backwards. Let me ground these together first so I don't blow something up. It's a big capacitor. Yep, it's good. Okay, so we'll hook the positive up to the positive of the capacitor. And here's a wire. Hook the negative of the capacitor to the negative side of the diodes. And I'm going to try to crank at roughly the same speed. And look what we get. Nice, flat, DC line. The capacitor is really quickly acting like a battery, but a super fast battery, and it's charging up during the peaks and discharging during the drops. But let's take it a step further. Now let's replace our capacitor with a battery. So I got a little lithium iron phosphate battery here. Do not want to hook this up backwards. Okay, so there's the ground. And here's the positive. Let's bring another toy into the mix here. We've got a current meter. I'll set this for DC current. Put that on the wire going to the battery. Hope you can see that, but I'll read it out to you. And let's start it up and crank again. Notice that the DC voltage is up there already. I'm going to move the reference line up to it because the battery is actually producing voltage, because that's what batteries do. So I'm trying to center that right in there so we can see the difference. which is telling me that this is putting out 13.4 volts, more or less. I didn't calibrate stuff up. And, well, let's give it a go and see what happens. As I go faster, I'm starting to feel a load, and you'll notice how those sine waves are flattening out. And when we look at the current, we're getting like 0.8, 1. You know, as I go faster, I could probably get it. There's 2.5 amps for a little bit. Whew. Well, I don't want to do that very long. That would be no problem, though, for the propeller shaft. It spins way faster than that. And since I'm merely a human and I don't have 1,000 square feet of sail pulling me through the water to generate the power, essentially for free, I'm going to switch down to one lithium iron phosphate cell. This is just 2 point whatever volts. So let me put that in place. Everything's the same, except now I don't have to crank so fast to make the same voltage. Again, I'm going to bring the cursor down so we can see the difference. This is putting out 3.3 volts, it says. And let's give it a crank. Oh, I can feel that right away. I'm putting out 1.5 amps, and I can feel it. I'm going to try to go faster. That's 3 amps. The voltage is coming up ever so slightly. There's 5 amps. So 5 amps at 3 volts, 15 watts, but you know, I'm all bent over sideways. I think that's cool. That's proof of concept. This thing, this stuff on the desk, if we put some kind of mechanism that would take some free power, whether that's the wind, the water going by the boat, I don't know, a horse on a treadmill, whatever you want. If you can make that spin, even at a reasonable speed, you now have the facility to turn that spin into electricity that's charging a battery. I still get a little thrill when I do this kind of stuff. It's fun to have physics actually work. And there was a long period of time back when solar panels were like crazy expensive and I didn't have any place to put them on the boat. I ran my boat almost exclusively off wind power through one of my axial field alternators. Again, there's an old video for that. That'll tell you how to do everything, including carving your own blade. If you live off grid in a house in a windy area, especially if you're up north, wind is still viable. And when you're on land, making a big 3-blade wind generator can be quite cost effective. And honestly, it's one of the coolest projects. When you make power off a generator, it's like, yeah, I bought it. I bought gas. I put it in it. You're just an operator. You know, you're not tied to it. When you make power off solar panels, you know, you had to wire it up and stuff. So you feel like that power's more your own, more personal, you know. But if you do a wind generator project, I guarantee you will love that thing forever. When you actually carve the blades, do the math, design the alternator, that is the most personal power. And every day when you use that electricity, you really appreciate it. This stuff is just fun. Hope you enjoyed the video. We're gonna go a little deeper. I don't like the diodes. So I'm gonna try to build some active circuitry that can do this work with modern transistors. And it can do things that this can't even dream of doing, theoretically, but I haven't tried it yet. That'll be in the future. Tell me if you like this. Leave me a comment, give me a thumbs up, and by all means subscribe. I really, really want to hit that 100,000 number this year. Bye from Clark on Temptress.